This is a Cedric rafter counting chamber, which is commonly used for water analysis and culture inspection. The chamber holds a known volume of liquid, 1 milliliter, which is representative of a larger volume from the source. For example, samples of sea, river or lake water can be prepared and examined under the microscope to help you identify algae or zooplankton populations. The technique was developed in 1889 by William Cedric and George Rafter, who were studying the purity of drinking water. It was their findings that led to the chlorination of drinking water. The base of the Cedric rafter can be plain or gridded. This one is plain, but Graticals Optics manufactures both types. The plain version is used with a Whipple or index grid in the eyepiece of the microscope. This method does require you to know what magnification you're operating at, so you can calculate the volume of the area covered by the grid in the reticule. But with the gridded version, the square pattern acts as your measurement guide. It's handy for use with a stereo zoom microscope, as you don't need to set up the precise magnification before counting the sample. There are 1,000 squares across this 1 milliliter chamber, with each square marking a volume of 1 microliter. I'm going to show you how to prepare a sample. The cell can be used with either living or preserved material, but the most important thing when filling the cell is not to overfill or to trap bubbles inside the chamber. To prevent this, we're going to put the cover slip across the chamber at an angle, like this, and allow it to fill from one side and the air to escape from the other. I've mixed the sample to ensure an even distribution before measurement. Using a wide neck pipette, we take up at least 1 milliliter. Now keeping the pipette nice and flat, filling from this side, we fill, allow the air to escape from the other side, and then turn to seal the chamber. We need to be careful not to overfill the chamber, or else the cover slip could float free. It's the surface tension that holds it closed down to the cell wall. Before we can do a cell count under our microscope, the Cedric rafter needs to be left to settle for 15 minutes. If your microscope is LED illuminated, it might be cool enough to leave the cell on the subject stage. But if you're using a halogen bulb, it might get too warm and cause small air bubbles to form underneath the glass cover. To prevent bubbles forming, add a small drop of distilled water to the edge of the chamber wall. This will prevent it from happening. Now that our sample has settled, let's have a look under the microscope and do a count. You can see this is a live sample, which obviously can prove difficult to get an accurate count. The protozoa are moving around and swimming within the 1 milliliter depth of water, moving in and out of focus. We need to preserve and stain the sample to prepare it so that everything stays still. Lugos iodine is a good agent for this. Although it can be detrimental to some samples, it's not causing cell wall damage to these protozoa. We're going to concentrate on one square where we can see 3 protozoa, and the square to the right has 2. So that's a total of 5 across 2 squares, which means an average of 2.5 per square or 2.5 per microliter volume. There's also a second species of protozoa seen across these 2 squares. We'll call it type B, which means its average population is half a protozoa per microliter volume. Scaling up our count, we'll do some maths. Based on the fact there are 1,000 squares in the chamber and there are 2.5 type A protozoa per square, means there are 2,500 in 1 milliliter chamber. So that's 2.5 million in a litre of the sample liquid. This is really simplified, as you would count and average more than just 2 squares randomly across the chamber, and you'd also test more than one sample to ensure you get a more accurate average.